Hello, in this video we will talk about enthalpy changes, particularly Hess's law. So the ultimate outcome of Hess's law is that the enthalpy changes for chemical reactions are additive. So let's take a step back and figure out why we would want to do this. So we talked about enthalpy changes and how that can be listed for a reaction, and at constant pressure this tells you the heat that's released by a reaction. So that's very useful information to have. And if we add this little bit of theory behind our knowledge of enthalpy changes, we can make this a lot more useful, and we can broaden this kind of knowledge to many more conditions and states and places where we want to know what the enthalpy change is. Okay, so let's show this with an example. So you've already seen how we can write a chemical equation, and then next to it write the enthalpy change for that reaction is equal to some value of kilojoules per mole. So that's what we're doing here. And now we're showing off two different reactions. One where you take tin plus 1 molecule of chlorine to make tin 2 chloride, and then another one where you take the same tin 2 chloride plus another molecule of chlorine to make tin 4 chloride. Okay, so let's try adding these two reactions together. So you can add chemical reactions just like you add mathematical equations. You treat the reaction arrow like it's an equal sign, and then you add everything that's on the left and put that on the left side of the arrow, and you add everything on the right, put that on the right side of the arrow. So we're going to take the tin 2 chloride, and then 2 molecules of chlorine gas, and put that on the left, and then we take tin 2 chloride and tin 4 chloride and put that on the right. Now we can cross out the tin 2 chloride, because that's present on both sides of this reaction arrow, just like you could cross out a term that's present on both sides of the equal sign in a mathematical equation. And that gives us reaction 3. Okay, so we just added these two chemical equations together. Now, what do we get for the enthalpy change of this new chemical equation? Well, to find the enthalpy change value for reaction 3, we can add the enthalpy change for reactions 1 and 2. And so this is what Hess's law tells us in a nutshell. So, to find enthalpy change for 3, let's add 1 and 2 together. And when you do this, make sure to respect the signs of the enthalpy changes. So this is negative, and we don't want to lose that when we do this math. And so you just add these together, and you get this value for the overall enthalpy change for reaction 3. And great, you can now list this with the equation and move on about your life, having figured out what the enthalpy change is for this new reaction that you never had to measure in the first place. You can look at reactions you already know and then figure out what the enthalpy change would be for reactions that you don't know, you can't run, you don't want to run, things like that. Let's visualize this. So in this example, reaction 1 is here, and this is decreasing the overall internal energy of the system when you release heat. And so we're going to drop down to a lower energy state here. And then reaction 2 is dropping down to an even lower energy state. And so you can do this in either 2 steps, or you could just shortcut this and do this all in 1 step, and that's what reaction 3 was telling us. And this is, in essence, what Hess's law says. So, the overall change in enthalpy is the same, whether the reaction takes place in 1 step or multiple steps. And this is all possible because enthalpy is a state function. It only cares about final and initial states and doesn't care how you get there. You could get there in 1 step, 2 steps, whatever. The overall enthalpy change just depends on final and initial. Okay, so when we apply Hess's law, we wind up manipulating equations in order to get the answer we want. And so when we're manipulating equations, we need to adhere to some rules. And so these are not necessarily part of Hess's law, but this is the first time we wind up doing this, so we have to talk about this now. Now, when you're playing with equations, make sure you specify the physical state involved, because a gas has much different energy associated with it than a liquid. So if you burn propane and write your equation to make gaseous water vapor, that's one energy associated with it. Whereas if you write your equation to make condensed water droplets, that's a different enthalpy change associated with it, because there's some enthalpy change involved in going from water to gas. So gas versus water really matters here when you're talking about energies. It doesn't matter when you're talking about how to balance the equation and things like that, but we care about energies at the moment. Now, if you multiply both sides of an equation by some factor, then also multiply delta H by that factor. This makes sense. If you have to put in this much heat to vaporize water, well, if you vaporize 4 times as much water, you have to put in 4 times the heat. So that makes a ton of sense. Now, if you reverse an equation, then you have to change the sign of delta H. Because if you have an endothermic process, like you have to put heat into water to vaporize it, to boil it, well, the reverse of that is an exothermic process. If you take gaseous steam and condense it into liquid water, this releases a bunch of heat. And so if you reverse an equation, which we often do in working with problems related to Hess's law, if you reverse the equation, then you have to change the sign on delta H. Now, let's do a couple examples. So, say you have this equation, graphite plus half an oxygen goes to carbon monoxide, and you want to know what the enthalpy change for that reaction is, but it's not a reaction that you can physically do in the lab or that's feasible for you to run, etc. So this is unmeasurable. So we want to figure out what this is. We do know that graphite plus oxygen to make CO2 has this enthalpy change value, and then carbon monoxide plus half an oxygen molecule goes to CO2 has this enthalpy change value. And we're going to leave this half of an oxygen just as it is, because that's how the material is presented to us, and it makes the problem easier to solve. Okay, so now this is just like a word puzzle. The heck with Sudoku, or a crossword. Play with the equations here and try to make it match the equation that you're aiming at, and it's kind of just a fun puzzle. So looking at this, my goal is to get graphite on the left side of the equation, and reaction 2 has graphite on the left side of the equation, so I'm probably not going to reverse equation 2, because it already has graphite in the right spot. The oxygen, well, there's oxygen on both, on the left side here, and then we'll see it come up later too. But now carbon monoxide, that's present on the right side of our goal equation, but it's present on the left side of equation 3. So we're probably going to have to reverse equation 3. When we do so, this carbon dioxide will be a reactant, this carbon dioxide will be a product, and then they'll cancel out, which is good because there's no carbon dioxide in our eventual goal equation. So let's try that. Let's reverse this reaction. And when we reverse the reaction, remember we changed the sign on the delta H for that reaction. So now this is positive 283. Then reaction 2 is unchanged, so we're just going to copy it down here so we can see it again and see what we're doing. Now, since we've reversed reaction 3, we can just add these together, and in doing so, the carbon dioxide is going to cancel out, and then half of an oxygen will cancel out, and it's going to leave us with half of an O2 right here, and then that gives us the equation we're looking for. So here's the sum, and that's perfect. That's what we're aiming at. And then now the enthalpy change for reaction 1 is equal to the sum of the enthalpy change for reaction 2 plus our now reversed value for reaction 3. So you add these two together, and then you get this answer down here, and that's your enthalpy change for reaction 1. Perfect. We solved the puzzle. Then let's show an example of this visually. So the reaction that we're aiming at, reaction 1, was right here. And so what we did is we knew the value for reaction 3 and reaction 2 and used that. We took reaction 2 and subtracted reaction 3 from it in order to give us reaction 1. Alright, one last example here. And this is just kind of a cute example to show off the overall process of Hess's law. So we're trying to match this equation on top based on these two reactions on the bottom. And right away I see that reaction 1 here has D on the left, but ultimately I want D on the right. The same is true for E. I want it on the other side that it is present on equation 1. So I'm going to reverse this. And then feel free to just write this down and play with it. So let me rewrite this. Okay, So now, since I reversed equation 1, we have a negative sign here, because you change the sign whenever you reverse an equation. Alright, now am I any closer to the goal? Well, I see that we have all the right components on the right sides of the equation, of the reaction arrow, so I don't need to do any more reversing of reactions. But I've got the wrong numbers of things. I see that I only have 2a down here and 6a in the goal. So that means I'm off by a factor of 3. And hey, look, I need 3b, which is also off by a factor of 3. So let's try that. Let me multiply this equation down here by 3. And when you do so, you now have the enthalpy change times 3. So let me rewrite that through the magic of video. So we multiply all the coefficients in the second reaction by 3, like so. And then we multiply the enthalpy value by 3 as well. And now, right away, I see that 3c is present on both sides of this reaction arrow, so it's going to cancel out. And then, actually, all the other coefficients match our goal equation. So let's write the ultimate outcome here. So we just add these two equations together, and it gives us 6a, 3b, and then the 2d plus 3d makes 5d, and then there's e. Perfect, so this matches the equation we're aiming at, as given in the problem. Then the enthalpy change is the opposite of reaction 1, so just multiply it by the negative sign, and then 3 times the enthalpy change of reaction 2. And it turns out that's one of our options, that's D up here, and thus we've solved the problem. So in addition to just reversing and adding the equations together, you can also multiply the stoichiometric coefficients by some number consistently, and that works out just as well. Okay, so that's what we have for Hess's law. Thanks very much for watching, and we'll see you again.